Okay, in the last recording, we looked at using rectangles to estimate the area under curves. Now we're going to apply the same type of reasoning to a real-world example. Here it says the velocity function of a projectile fired straight into the air is f of t equals 140 minus 9.8t meters per second. Use the summation technique just described to estimate how far the projectile rises during the first 3 seconds. How close do the sums come to the exact value of 435.9 meters? Okay. Now we're looking over a 3-second interval. What we're going to do is we're going to look, at 0 seconds, at 1 second, at 2 seconds, and at 3 seconds. Okay. So at 0, 1, 2, and 3 seconds. Now if I knew how fast it was going at 0 seconds, then I could estimate, let's just estimate that it goes that far for 1 second. Then how fast is it going at 1 second? We can say, well, let's estimate that it's going that fast for the next second. And then at 2 seconds, how fast is it going? Then we can estimate that for the next second, okay? Or we can use upper estimates, okay? So we can estimate that it's going whatever the speed is or velocity is at 1 for the first second, and whatever the velocity is at 2 for the second second, and the velocity at 3 for the third second. And that will give us both an upper estimate and a lower estimate, okay? Now, let's just do f of 0 first, which is 160 minus 9.8 times 0. Okay, 9.8 times 0 is 0, so that's just 160. So at this second, at the time 0, it's going 160 meters per second. Okay, now how fast is it going at 1? Well, at 1 second, it's going 160 minus 9.8 times 1, which is 160 minus 9.8, which is 150.2. So at this first second in time, at time 1 second, it is going 150 meters per second. Now let's look at 2 seconds. At 2 seconds, it's going 160 minus 9.8 times 2. That's 160 minus 9.8 times 2 is 19.6. Subtract there, and that will be 140.4. So at this time, 2 seconds, it's going 140.4 meters per second. Okay, well, how fast is it traveling? At 3 seconds. Well, that would be 160 minus 9.8 times 3. 9.8 times 3 is going to be 29.4. And we subtract here, and we will get 130.6. Okay. Now we want to estimate that over this first second, okay, this is going to be a lower estimate, that over this first second that we're going 160 miles per second. So if we're going 160 miles per second for 1 second, then you will have traveled 160 miles. Plus, let's estimate during this second interval that we're going 150.2 seconds. So you've went 150.2 for 1 second, so you've went 150.2. And then let's estimate for this second. And let's estimate we're going 140.4 for that second. And for 1 second means you've traveled 140.4 seconds. Notice I didn't use this. I'm looking at just my lower estimates. If you go ahead and, of course, multiply each one of these by 1, you'll get 160, 150.2, and 140.4. Add them up, and you will have 450.6. So our estimate there is that we have traveled 450.6 meters. Now, if I do the estimate from the other end, if I estimate that for this second I was actually going 150.2 meters per second, that's 150.2 at 1 second. And then for this second I was going 140.4. And then for the third second I was going 130.6 meters per second. Now notice I'm doing times 1. These intervals are each a length of 1, but if I had made the intervals a length of a half of a second, or some other interval not 1, I would need to make sure that I was multiplying by that. Now multiply, add up, that will be 421.2 meters. Now the actual exact value is 435.9, which you can see is just kind of right in the middle of these two estimates. Okay, so the estimate is about, say 14.7 less than this, and it is about 14.7 meters more than this. So it's the value that's right in between the two. So this is just a real-world example that uses that same kind of a concept that we were using to find area under a graph. Now this gives us more and more intervals. Of course we did 3, but as you do more and more and more intervals, you can see you get closer and closer and closer to that actual value of 435.9 was the actual value, so you're getting closer and closer and closer to actually being at 435.9. Now the other concept we want to discuss in this section is the concept of average value. Now the average value of a function on an interval is the area divided by its width. Now if you look at graph A where you've got a rectangle, well the area is a rectangle, and it's what you get when you take that area and you divide it by the width, which is B minus A. Now it would be fairly easy to do to find the area for a rectangle. If you look at the graph of g of x, graph B there, it's not quite as easy to find. But if we want the average value on a graph, then we take the area of the graph and we divide it by the width of our graph. Now this is a really easy example because we can easily find the area of this graph. We know if we're doing the area of a rectangle, then that's 1/2 base times height. So here that's 1/2, and we'll see our base is 2, and since our graph is f of x equals 3x, our height is 6. So times 2 times 6 is going to give us 6. So our area is 6 square units. Now if you want to know the average value, then you take that 6, the area, and you divide it by the width here, which is 2 minus 0, or 2. The width of this area is 2, and so that's 6 divided by 2 is 3. So 3 is the average value over this interval. See this line 3? That's the line y equals 3. That shows us the average value of this graph over the interval. Now here we have f of x equals sin x, and we can't just easily find the area under here. Now let's say we used 8 rectangles like they have here to approximate the area. Then the area that you would find would be approximately 2.365. Now we're not going to take the time to actually do that, but remember we could do that just by taking, this is width of pi over 8, what's the height, pi over 8, what's the height. We could find our area in that way, okay? So this is just an approximation. If we want the average value of our function, we'll take that area, which is 2.365, and we would divide it by the width. Well, if I'm going from 0 to pi, the width there is pi. So I would divide by pi, which would give me approximately 0.753. Okay? So 0.753, which would be somewhere right in here. That's the average value of this graph.